Let's take a look at another example of trying to prove or disprove a relation being reflexive, symmetric, and transitive. So we have this relation. It's going to be given by either the first number is equal to the second or it's equal to its negation. And this is going to be defined on the set of all integers. We'd like to figure out if this is reflexive, symmetric, and or transitive. So let's look at reflexive. We ask ourselves, for every integer, does it equal itself or does it equal the negative of itself? Well, since this is an or statement, again, one of them just has to be true. So we're thinking that yes, this is going to be reflexive. So we have our proof of what this looks like. So if we say, let x be an element of z, we see that x is equal to x, which implies that x comma x is an element of R. So we have shown that for every element, because it is equal to itself, because this is true, that is going to be in our relation. Great. That's our proof for that. So then we have symmetric. So here we're figuring out, okay, so if this is true, so what numbers could this be that would work in this? So for instance, 1 is related to 1, right? So then if I flip those, is 1 related to 1? Well, yes. But 1 is also related to negative 1 because of this part here. Is negative 1 related to 1? So if I switch those, does that also hold to be true? Well, yes, that also seems to be true. So, indeed, this is going to also be symmetric. So we have this proof. So we could say, let x and y be elements of z such that x, y is an element of R. So we're picking these integers that are defined in my relation. Okay, so now I'm trying to figure out why is it true that y is going to be related to x? Well, again, we can unpack this using what this set is defined as. So if x is related to y in this, so since x, y is in R, this implies that x is equal to y or x is equal to negative y. All right, so we know this from our definition of it being in this set R. So since it's in this, that means x equals y or x is equal to negative y. Now to show that yx is in there, well then we have to show that y is equal to x or y is equal to negative x. Well here, does y equal x or y equal negative x? Well, yes, we should be able to see that that's true from here. So since this is true, this implies this. We see this implies that y is equal to x, or if we multiply this by negative 1, we see that y is equal to negative x. Hence, yx is in my relation. So then that proves this. So we start out with something that is in our relation, show that if you switch the ordered pair, that stays in the relation. So then the last one here is transitive. So you're thinking about examples in your head. So for instance, 1 is related to negative 1. Negative 1 is related to, say, negative 1. Is 1 related to negative 1? So we have this train of them. And so doing some examples, you should convince yourself that this is going to be true. So we have the proof of this. So if we say let x, y, and z be elements of z such that xy is in R and yz is in R. So again, we start out with this assumption that we have these elements in our relation. Our goal that we'd like to prove is that xz is in R. So again, we unpack these using the definitions. So then since xy is in R, this implies that x is equal to y or x is equal to negative y. Similarly, we see that y is equal to z or y is equal to negative z. So again, they're just the same types of ideas of unpacking these, so I can just simply state that. Now, when we think about how we could really prove this, you might start to convince yourself that this is true, but you might be thinking, how do I actually prove this? So one way to do this is you could structure proof by cases, right? So you could have the case where maybe x is equal to y, and then y equals z, then x equals z. Or you could do x equals y and y equals negative z, well, x equals negative z. Or you could do x equals negative y is equal to z, therefore x is equal to negative z. So you could do all of these proof by cases if you would like. And so you could structure your proof in that manner. Or you could try to come up with something a little bit slicker to figure out what this would be. But in this case, I'll be honest, it's not really designed to be super crazy in depth. It's really just helping you get accustomed to thinking about transitive. So in this case, the results were just hopefully easily convinced by. So in any of these cases, we see either x is equal to z or x is equal to negative z. So, for instance, on homework questions, you might be asking, can I ever do that? Because that seems like I just skipped a whole bunch of the proof. Ask me. I'll be happy to tell you if it's really important that you show me all of the details, or you can just say something simple like this that just summarizes all of it. But now that we see that in any of these cases, x equals z or x equals negative z, hence x z is in my relation. So we have now shown that this relation is reflexive, it is also symmetric, and it is also transitive. And so this is very important. This next definition, this next phrase will continue to follow you in some of your later on math courses. So we have the following definition, that if a relation is reflexive, it is also symmetric, and it is transitive. If a relation, then this is an equivalence relation. So this is the definition of an equivalence relation. Equivalence relations are the nicest, best type of relations to work with. You're going to hope to have equivalence relations when you're trying to prove things, because a lot of things that we're used to thinking about are just, it's very natural to think about things being related to themselves, things being related to, if one is related to the next, then that thing's also going to be related to the other, and then there's transitive property. So this idea, this relation that we just defined, this is an equivalence relation. If you just simply look at the relation defined by equals, that is also an equivalence relation, right? So if we think about a number is equal to itself, if you think about one number being equal to another number, if you switch them, that's still true. And then if one number is equal to another and that's equal to another number, then we have that the first is equal to the last. So this equivalence relation is very nice to work with. So when you go ahead and you take modern algebra next spring, you're going to have some very important proofs that are based entirely on equivalence relations, hoping that things are reflexive, symmetric, and transitive.